welcome to the video lecture series brought to you by St. Andrews Institute of Technology and Management. My name is Ravinder. I am an assistant professor with ETC department, and we are discussing the subject called Data Structures 2 or Advanced Data Structures. And yesterday we have seen in the lecture what are the traversal techniques in a binary tree, and before that we have introduced a new topic called binary search trees. And today we are going to see the algorithm of binary search tree, that is algorithm which will guide you to how to write the code for searching a particular item in binary search tree. Okay, so I'm going to directly head you back to the algorithm, and I will tell you how it goes, and we'll take the example we have taken in the last lecture. Let's say this particular example, and I'll guide you. That is, I will try to show you how we actually want to proceed. Okay, so let's start with the algorithm. So this is your algorithm for searching a particular item in your binary search tree. Okay, now let's head back to the first line, that is the signature of the function. The signature of the function, or that is the algorithm which you will in future develop into a function or method. That is, so what it requires is the info, the left, the right, the root, the item to be searched, the location, and the parent. Okay, what are the meaning of all these things? I think three of them are pretty clear. That is the root and the item to be searched and the location of the parent and all that. Okay, so everything else will make sense as we proceed towards the algorithm. So before starting with the algorithm, let me tell you that we will have three scenarios on the basis of which you're going to decide or we have decided to write this particular algorithm. Now in binary search tree is in the memory, and if an item of information is given, then this particular procedure finds the location of item in a tree, let's say T, and also the location of its parent, that is PAR of the item. Okay, now we have three special cases. The first case is, what if the location is null? That is LOC equal to null. Now LOC points to the very first node of the tree, and let me remind you that very first node of the tree we have discussed yesterday also. In a binary search tree or any tree would be your root node. Now if location is equal to null, it means your tree is actually empty. It has no nodes in it. That is your first case. Okay, it has no nodes in it. In that case, you cannot search anything because your tree is already null. There is nothing in it. So what you are going to search in? So the first line of your algorithm test that particular case, that is, if your root is equal to null, then set location equal to null. Let me remind you, this location will tell you the last location of the item to be searched. So the pointer location and the pointer PAR, that is parent, are actually the parameters that are going to be returned by this particular algorithm. So these two parameters will tell us the exact location of the item to be searched and location of its parent of the item to be searched. Okay, now if root is equal to null, then we have nothing more to do. Set the location of the item equal to null, it means it is not there, and set its parent's location also equal to null. So that's some particular other helping method doesn't understand that, okay, the item is not in there, but its parent, or you can say the tree does exist. Okay, so in this case the tree does not exist because it doesn't have any node right now, and then your method will return some value, that is the value of the LOC and the value of your parent. Okay, now what is the next case? Now next case is, what if your location is not equal to null and your parent is equal to null? Okay, in that case it means that your item is actually the root. Your item is actually at the root. Okay, let me head back to this particular item. Now as you can see, this is your root. Okay, now if I say that your item is actually this one to be searched, that is you want to search 25 and 25 is actually residing in the tree to be searched at the root level. So in that case, the location which is going to be returned is the location of the root, and its parent is actually null because roots don't have any parent. We have discussed it yesterday. The pointer to the root, or the parent pointer to the root node will always be equal to null. Okay, so this is our second case. Now if item to be found is actually compared and found out to be at the root, then location of the item to be searched is equal to the location of the root, and your parent will be equal to null because roots doesn't have any parent, and then your function or your method will return. Okay, so the second condition satisfies. So first condition is there is no tree at all. The second condition is yes, tree do exist, but the item that you want to find is actually in the root node itself. Okay, I think you have got the point what I am trying to say. Now the third case. The third case is the location is not equal to null, and your the location is equal to null and your parent is not equal to null. Okay, it means your item is actually not inside your tree. Your actual item is not inside your tree. So what I am trying to say here is that parent, suppose you want to find out the value that is let's say 11, then what will you do? In the layman terms, we'll first compare the item with the root node, that is 25. 11 is less than 25, so we'll go to the left hand side. The standard rules of your binary search tree, smaller items will go towards the left hand side, and larger items, then the parent will go to the right hand side of the child. Okay, now it will compare the value with 15. Again, the value of 11 is less than 15. Again, we'll go to the left hand side child. Now it will be compared with 10. Will go through to the right hand side. Now it will be compared with 12. Now as you can see, we cannot go towards the right hand side, right or left hand side of the 12, because the this particular node, that is 12, is actually a leaf node. Now if it is a leaf node, that means if the element do exist at some time, not at present, at some time, it must exist at this point, not at any other point. But because it is not there, we'll set the location of the item equal to null. That means it is not in the tree, but parent has been found. That is, if you want to add that particular item, if it is not there, and if you want to add that particular item, then you can add at this particular node, that is 12, because according to the rules, that particular item, that is 11 in this case, in this example, cannot be added at anywhere else. I think you have got the point what I am trying to say. So our searching algorithm is actually laying the foundation of the addition of a particular item. Sorry, the addition of a particular item if that particular item is not found in your algorithm already. Okay, so it has laid the foundation of that already. So we're going to see the addition and deletion of a particular node in BST tomorrow. But if we have understood the searching algorithm exactly or correctly, then that going through that, those two particular algorithms will be piece of cake. Okay, so now we'll turn up to the next scenario. That is the scenario where location is not equal to null and your parent is also not equal to null. It means that okay, that element do exist in your tree, but we have to find it out. And find it out how? By using the rules of binary search tree. That is, we'll compare the item to be searched with each node and if it is that node, the location will be returned, location of its parent will be returned. And if not, if that is not the value you are searching, then according to the value of the item and value of the node you are searching, you have to decide either to go left or to go to the right hand side. So I think you have got the point what I am trying to say. So let's come back to the third point. Now if the item is less than your root, then simply put, your pointer is now heading to the left hand side, because your item you are searching, like if we go in this case, we have to search for item 11 and it has a value less than 25, that is your root node. Then your pointer will head to the left hand side of the tree, subtree, okay, not to the right hand side. So this third point actually setting up the context of further search. Okay, and if the item is actually not less than the root value, info means the value at the root. Okay, don't get confused. Info means value at the root. Okay, so in that case, the pointer will head to the right hand side, actually, to the right hand side of the tree. Okay, like in this case, if I want to search some value which is actually more than 25, then my search algorithm will actually, if not at the root, will actually look to the right hand side, not to the left hand side. So I think you have got the point. Now let's move ahead. Now comes here the loop. Now this loop will not stop until we have gone through the whole tree path. That is the path which we are allowed to go to according to the rules of the BST. That is left, right, left, right, left, right. And it will not stop searching until it has reached to that particular item or reached to the leaf node. Okay. So what will happen is, now if item is equal to info pointer, then set location equal to pointer and pointer equal to save. That is, you have reached to either to the left hand side node or to the right hand side node of your root. That is, after we have moved here, compared that, we have found that item is not this particular root. So in that case, either we have moved to the left hand side child or to the right hand side child. If item is one of them, in that case, all we have to do is set the location equal to new pointer, which has been again set it to the either to the right hand side or to the left hand side of the root. Okay, and parent is equal to save. Save means root. Let me remind you, in the last particular item, or the last step, that is third step, in the save variable, we have saved the location of the root. Okay, so now the parent, the item that is inside the save is now in the parent. So basically root is now in the parent. So this is the case where the left hand side child or the right hand side child of the root is actually the item we are looking for. And if it is not, then we will again apply the rule, that is, we have to compare the item either with towards the left hand side child or to the right hand side child, depending on the path that we have chosen in the step third, with the parent item, and then we have to look if we have to go right or to the left. Okay, so that is what has been done here in the sixth line. That is, now if item is less than info pointer means, suppose we are headed to the left hand side. We'll talk about this side now. We'll take the example 11. Now 11 is not 25, so we have headed to the left hand side. Now we are at this point. So info pointer is actually fetching out the information that is residing in this particular node. That is 15 actually. So if item is not equal to 15, that is what it is saying is, in the sixth point, it is saying that if your item to be searched is less than the info at the pointer, and in this case is less than 15, then what we have to do, we have to go to the left hand side of this particular item, left hand side to this pointer. Okay, so this is what we have done is, we have saved the value of the pointer and in a variable called save, and the new value of pointer, that is the value of pointer, will be updated to the left of the pointer. So don't get confused. Now pointer is currently pointing to this particular node, that is 15. the new value is to the left of this pointer. To the left of this pointer is node 10. So now your pointer is actually pointing to this particular node. And inside the save variable, we have the address of this particular node. Okay, so you have got the point. We have to update both of them, that is location of the pointer as well as location of its parent also, because our algorithm is supposed to return two items, that is location of the item as well as location of the parent of the item. Okay, so we have to track both of them. So let's move ahead to the last point. If that is not the case, that is else, then it must be, the value must be greater than 15. In that case, what we have to do, we have to save the location of pointer in a variable called save, and the new value of the pointer will be 22 instead of 15, that is to the right of the pointer. And this is what we have written here, that is pointer is now pointing to the right hand side of the old pointer location. Okay, and we will do this, that is the item 5 and 6 will go through this process again and again and again until while your pointer is not equal to null. And when the pointer will be equal to null, when you have reached to the leaf node and your item is still not found. In that case, it has been understood that your item is not in the tree, but you have found the parent. This is what we have discussed in the starting, that in that particular case, your search algorithm will tell you that your item is not inside the tree, but if you want to add it, that is if you want to add that particular item as a new node in your tree, in that case we have found the exact location where according to the rules of binary search tree we can add that particular item. That is in case of your example 11th, we have found that it could be added to this particular node 12. Okay, so this is what it is saying in the last line. This is what is saying. It is saying that location has been returned as null. That means your item is not in there, but your parent's value we have found out. If you want, so if you want to add a particular, let's say item in your binary search tree, then this particular algorithm, that is searching in BST, is actually, you have to run that first. Okay, you will see in the next lecture that for finding, that is for adding a particular item in your tree, you actually have to look for it first. It doesn't mean that you have to look for its copy. It means you have to look for exact leaf node on which you can add your particular item. Okay, so this searching algorithm is actually of dual use. It is actually finding out the item to be searched if it is in the tree, and it is also telling you it is also going to tell you the exact location where you can add that item if it is not already in there. So I'm going to end this lecture here now. You can pause that video and write this particular algorithm. It is quite easy to visualize when you see a particular example of tree and try to visualize how things are going on. Okay, in next lecture we're going to see how to add a particular node in your binary search tree and how to delete a particular node from your binary search tree. Thank you.